हॅलो. या मी येते घरी.
तू तो पुरुषोत्तम आहे.
Good morning, students. So in the last lecture, we started this chapter, transition and inner transition elements. This is also called as D and F block elements. The introduction part, then what is meant by D block elements. Once again, I'm also repeating the concepts of D block elements and F block elements meanwhile. But the basic concept should be clear, what is meant by D block elements and what is meant by F block elements, because we can see in the periodic table. I will show the periodic table again. This is a just quick revision, because many students forgot what is meant by D block elements. See, these D block elements which are kept in between H block elements and P block elements. These P block elements are extremely right hand side of the periodic table. These are also called as electronegative elements. So P block elements are also called as electronegative elements, and these H block elements are electropositive. So in between this H block and P block, the intermediate or the transition elements are called as D block elements, which starts from this scandium, group number 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are the capacity of the d orbital is 10 electrons. So there are 10 groups in the periodic table. So this is a 3D series because electron enters in 3D. So this scandium to zinc, this is called as 3D series. Then yttrium to cadmium, this is called as a 4D series because the electron enters in 4D orbital. Remember, if you write the electronic configuration of this scandium, yttrium, then I'm coming to this is a 3D, 4D, 5D series. 5D series, remember one thing, it starts from lanthanum and it ends with mercury. But in between this 57 to 71, that is 58, means atomic number 58 to atomic number 71. There are 14 elements, and these 14 elements are not included in this D block elements, remember. These elements contributes the F block elements. These are also called as inner transition elements. So these 14 elements which are shown below the periodic table from lanthanide to lutetium, these are not included in D block elements. Remember, once again I am repeating, lanthanum is included. These 14 elements are not included. So this is a 3D for 5D series, and from this 89 to 112, this 112, these are the newly discovered elements. Copernicum, this CN is called as Copernicium or Copernicum. This is a pronunciation of these elements. In the last previous textbook, the name was UUB, but now the nomenclature is done in, I think, in 2013. In 2013, the name of the compound Copernicium, it is given. So again, from atomic number 90 to atomic number 103, there are 14 elements which are not included in this D block elements, which forms actinide series. So this is a lanthanide series, actinide series. For the study purpose, only the first series is included for the syllabus of 12th standard. I also given the hint how to remember the scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. Out of these elements, it starts from 3D1, it is 3D2, 3D3, 3D4. Actually, it is a 3D4, but this chromium and this copper shows exceptional behavior because to obtain extra stability, one electron from 4s, it is shifted. So the observed electronic configuration is different than the expected. Observed electronic configuration is it is having the 3D5, it is also 3D5, it is 3D6, 3D7, 3D8, 3D9. Actually, it should be 3D9, but it is 3D10. It acquires extra stability. It gains one electron from 4s, so it becomes 4s1, 3D10. And this zinc, cadmium, Hg, and copernicium, I want to give information about these elements. This zinc, cadmium, mercury, and copernicium, in these elements, the 3D orbital is completely filled. Means 10 electrons are there in zinc also, in cadmium also there are 10 electrons, in mercury also there are 10 electrons, and this in copernicium there are also 10 electrons. So according to the new IUPAC definition of the transition elements, the new definition is the elements in which the d orbital should be partially filled or incompletely filled. These elements are called as d block elements, but these zinc, cadmium, and Hg, and this shows completely filled d orbitals. That's why these are not included in the transition series, remember. Then student will ask the questions why these are included in this series, as these are the last elements. Zinc is the last element in 3D series, then cadmium is the last element in 4D series. This mercury is having the last element in this 4D series, sorry, 3D, 4D, 5D series, and this copernicium is the last element in its 6D series. So for the study purpose only, these are included in the D block elements, remember. All these shows exceptional. These are not, as these are having the completely filled orbital. They also having the soft, very soft metals. The melting and boiling point is also less, but the atomic size is very large. Because in this zinc, cadmium, mercury, and this copernicium, as the outermost shell is completely filled, means all the electrons are in pairing state, remember. In case of chromium, if you see the chromium, 5 unpaired electrons are there, but in case of zinc, all the d orbital is completely filled, means the pairing is completed, and due to this pairing, the force of repulsion is more than the force of attraction. All these exceptional properties I have explained during the explaining the periodic trends, how the electronic configuration, then atomic size, ionic size, oxidation state is also very important. This is also explained in the last 2 lectures. Then different oxidation states of chromium, then cobalt, nickel, manganese. One important question I want to discuss here, because for board exam 10 times it is asked, say, which is that question? Yes. Why manganese, sorry, write the different oxidation state of manganese and why +2 oxidation state of manganese is most stable. Because if you see the outermost electronic configuration of manganese is having the atomic number is 25, and the outermost electronic configuration is 4s2, 3d5. So if these 2 electrons are removed from the s orbital, d orbital contains 5 electrons, and the 5 electrons means this is a partially sorry, what you can say, this is the capacity of d orbital is 10 electrons. So this is a half filled. If the d orbital is half filled or it is completely filled, it becomes stable. So if these 2 electrons are given from this manganese, the D will contain the 5 electrons and it will shows the stable complexes. So remember the manganese plus 2 having the stable oxidation state. These are the different oxidation states are already discussed. 3 marks question will be asked on it. So manganese shows plus 2, plus 3, plus 4, plus 5, plus 6, plus 7. All the oxidation states are shown by this manganese. So daily revision is required. Then this oxidation state of hardness, no question will be asked on hardness. But just I am discussing the trends in melting points. What is expected only for the student? This graph is not expected. This graph is given for your understanding only. If the question is asked for the board examination, it will be asked for 1 mark or 2 mark. And the questions are like this. Explain the trends of melting points and boiling points in transition metal. So just only we have to write down initially from scandium to chromium, the melting and boiling point is increases. In case of manganese shows exceptional in case of melting points, and again the melting and boiling point increases, and lastly again it will be decreases because no any unpaired electron is there in case of zinc. Initially why the melting points are increases, because up to chromium number of unpaired electrons increases. In case of chromium, we can see there are 5 unpaired electrons. So as the number of unpaired electron increases, what will happen? They will form the more number of covalent bonds, and if the more number of covalent bonds are formed, the hardness will increases. If the hardness will increases, the stability of the metallic bond will be increases. So it is a very high energy will be required to break this bond. That's why the melting and boiling point increases up to this chromium. But in case of this manganese, suddenly the melting points will be down because the structure of manganese is very complicated. This structure of manganese, structure of this what you can say technetium. So the explanation is given here. This explanation is not required at the board exam. This explanation is also not given in your textbook. So for the understanding this melting point part, I have given detailed information, but for the board examination only read this slide. In this slide all the information is given why after this chromium melting point and boiling point is decreasing. So for the students who didn't understand this slide, for these students, I have given this detailed information, how the number of unpaired electrons decreases and how the melting and boiling point will be decreases. Then this ionic and atomic and ionic radii is also explained in the last lecture, but within the 2 minutes, I will explain with the help of this graph. We can see from this scandium to zinc, these elements are placed in left to right. What will happen? Because these are not placed in a group, these are kept in a series. So in a period, what will happen? As the electron is added in the same shell, its effects occurs on the nuclear charge. If the nuclear charge will increase, so initially we can see here in this graph from this scandium. See, this is the scandium, this is a titanium, this is vanadium, chromium, manganese. So up to this manganese, we can see suddenly the atomic size decreases. We can see here atomic size will decrease because the nuclear charge increases. And from this manganese to this nickel, we can see there is a constant atomic size. This is happening because there are 2 effects. One is a nuclear charge effect and one is a screening effect. So from this manganese to we can see here in the graph, from this manganese to nickel, what is happening? The nuclear charge effect and screening effect is balanced. And at the end, in case of zinc, there is increase in atomic size because in case of zinc, you know, zinc, cadmium, and Hg, 3D, sorry, this is a 3D10, this is 4D10, this is 5D10. Means pairing will be there. There is no any unpaired electron is there. So due to this pairing, what will happen? The force of repulsion is there than the force of attraction. Means the force of attraction of the nucleus to attract the outermost electron, it is less. So in case of zinc, cadmium and Hg, the force of repulsion is more, and this force of repulsion is due to the pairing. The pairing takes place here. That's why the force of repulsion is more, and that's why the atomic size is more here. Remember, this is the reason. So only this is expected to write why initially it is decreases and then it becomes constant, and at the end why this is increases. So this is expected. These values, these graphs are not expected. That's why it is written here. One note is given, values are not expected from the students, only the trends are expected. So don't remember these values, don't remember this graph. This graph is shown only for your understanding purpose. So the ionization enthalpy, you know, many times we discuss about this ionization enthalpy. Is the enthalpy is also called as energy, amount of energy it is required to remove most loosely bound electron from the isolated gaseous atom. So this energy and atomic size, if the atomic size is very large, then sorry, the atomic size is less. When the atomic size is less, ionization energy will be more, and when the atomic size increases, ionization energy decreases. So there is a vice versa relation between atomic size and ionization energy, remember. So if the atomic size, ionization enthalpy values increases from left to right because atomic size is decreases. So this is not expected, only the trends are expected. Always, you know, the first ionization energy values are very high. First ionization energy values are less, as the amount of energy required to remove the second electron, third electron. So energy will be increased because the stability will increase. So we can see scandium values, I will explain here. In case of scandium, the first ionization energy value, means amount of energy required to remove the first electron is 632. And if you remove the second electron, the amount of energy will be very high. Again, the third electron, it is removed, the amount of energy will be very high because the stability increases, and if the stability increases, amount of energy required, it will be very, very high. So these values, first ionization energy, then third ionization energy is very high than the second ionization energy, and second ionization energy is very high than the first ionization energy. In 11th standard also we discussed these ionization energy trends in case of group number 13 and group number 14. Then this metallic character, this will be not asked for the examination, for the understanding purpose why these are transition element shows metallic character, because all the properties of metals these can show: malleable, ductility, good conductor of heat and electricity. Then they having the particular type of lattice structure. Different types of lattice structures are given. Then they also having the low ionization enthalpy values, covalent bond, metallic bond character. This magnetic property is also discussed, and then I am directly coming to this formula. Magnetic moment, this is ferromagnetism, diamagnetism is also explained in the last lecture. What is mean by paramagnetic substances? Paramagnetic substances means these are attracted by the magnetic field, they contain unpaired electrons. And the diamagnetic substances means the pairing takes place. These are not attracted by the magnet, these are repelled by the magnet. So remember, diamagnetic means the pairing is there, there is no any unpaired electron. And the ferromagnetic substances are the substances which are strongly attracted by the magnetic field. These are called as ferromagnetic substances. Ferromagnetic means the more number of unpaired electrons are there, then it is called as ferromagnetic. Remember, these elements are used for making the permanent magnets. Then this magnetic moment is calculated by this formula. This formula is called as spin only formula, remember. Many times for the examination, board examination, for the NEET examination, for the JEE examination, for the CET examination, 99% this question is there. So this magnetic moment mu, it is denoted by this symbol mu. The formula is n into bracket under root n into bracket n plus 2, and this is a unit. Bm is a Bohr magneton. This is unit of magnetic moment. So the magnetic moment depends upon the number of unpaired electrons. Remember, this n indicates the number of unpaired electrons. So how to calculate number of electrons? I will explain you. This one problem is given. Calculate the spin only magnetic moment of the divalent cation. Divalent means we have to remember it is M2 plus, means 2 electrons are given of a transition metal with atomic number is 25. So atomic number is 25 is given, means this is atomic number of scandium, titanium. Say scandium is 21, then titanium is 22, then vanadium is 23, chromium is 24, then manganese. So this is the 25, it is the atomic number of manganese. And if you remember, the outermost electronic configuration of this manganese is 4s2 3d5. As it is a divalent, means 2 electrons are already removed out of this. So we can see here 4s2, it is having the 0 electrons because it is removed, because it is divalent. So in case of this 3d, see the unpaired electrons 1, 2, 3, 4, 5, because it is 3d5. 4s2, 3d5, that's why unpaired electrons are 5. If it is 3d6, one electron will be pairing here, unpaired electrons will be 4. Then in case of 3d7, what will happen? Again, electron will pair, unpaired electrons will be 3. So after 3d5, the number of unpaired electrons will be decreases, remember. So if you know how to calculate the unpaired electrons, this value 5 unpaired electrons we have to put in this formula, 5 into bracket 5 plus 2, so it will be 7 into 5, 35 under root 35. This is the value 5.92 bm. Suppose if any student didn't know the process how to calculate this square root, we can write under the 35, half mark will be reduced only. Your half mark will be reduced if you are not unable to calculate the under root of it, but it is expected to calculate the unpaired electrons. It is also expected to put the values in this formula. It is also expected to write this unit also. If all these formalities are completed, then you will get the marks, but only the half mark will be reduced. So don't worry about the half mark. This half mark will be again converted into 1 mark after in that particular section. Number of half mark, if you get half mark, it will be converted into 1 mark. So my request to all the students, please fill the values and write the formulas. If you didn't do the mathematical addition, subtraction, division or multiplication, at least we should put the values in the formulas, then we will get at least 1 mark or 1.5 marks. Then I am coming to the color. So on the color, this is very important for the competitive examination. The D block elements are the colored in a solid form and in solution form. You know, just I will explain the introduction part of the color, how the substance appears colored, because any substance, if it absorbs the portion of visible light, you know, visible light means whatever the lights we are getting from our tube light, these are called as visible light. If any substance, it absorbs the portion of visible light, it becomes colored. If any substance do not absorb the light, then it will be appeared as a dark, or it will be appears as a black. So the color, it is depends upon the wavelength of absorption. Remember, what wavelength of light is absorbed and what wavelength of light is given. So the color will be depend upon what the wavelength of the absorption of the visible region. Means from the visible region, which wavelength is absorbed and which wavelength is transmitted. I'm coming to that point, transmitted. But first we have to remember the color depends upon the wavelength of the uh, absorption in the visible region of the electromagnetic radiations. Then these transition elements, we are discussing the color of the transition elements. These transition elements are colored in their solid form. In solid form also these are in colored form, and in also aqueous means solution form, these are also in colored. So these colors are due to remember there are four parameters are there. These four parameters can explain why these D block elements are colored. I will explain these four parameters. See, the color of the transition metals are due to these four factors are responsible. First factor is the presence of unpaired d electrons. If unpaired d electrons is there, unpaired d electrons, now we are familiar with this unpaired word, unpaired d electron is there, then it will be colored. Then second factor which is responsible for color is dd transition. Dd transition means this is the splitting of d orbital. Splitting of d orbital is also I explained in this chapter. Coordination compound. In case of coordination compound also I explained this dd transition. This is the second factor which is responsible for this color. So dd transition is the second factor. Then third one is nature of ligands. Now we are familiar with this word ligand because in coordination compounds I explained these ligands are the groups which are attached to the central metal atom which is having capacity to donate lone pair of electrons. So which type of ligands are attached to the metal atom? So the color is also depend upon the nature of ligands. And last one, the geometry of the complex which is formed by the metal ion, whether the geometry is octahedral or tetrahedral. So the color of the transition metals or the elements depend upon these four factors. So in your textbook only this first factor is explained, then third and fourth factor is explained. This second factor is not explained, but I will explain this all the four factors one by one. First one I am coming to the color due to the number of unpaired electrons. If the unpaired electron is there in the outermost shell, then if the unpaired electron is there in the d orbital, these elements are colored. If there is no any unpaired electron, it appears as a colorless. So with this table we can understand, first in the first column ion is given, this is outermost electronic configuration is given, then here the number of unpaired electrons are given, and this is a color is given. So scandium 3 plus, the outermost electronic configuration of scandium is 3d1 4s2. 3 electrons are removed, means 3 electrons are given. These 3 electrons will be removed, 4s2. So 2 electrons from this 4s2 and 1 electron from the 3d1. So it becomes 3d0. So there is no any unpaired electron, it becomes colorless. If there are 0 unpaired electrons, it will be colorless, remember. So in this case also titanium 4 plus, see it is 0 unpaired electron, it is colorless. So in case of this copper 1 means this is a see, this is a completely filled. There is no any unpaired electron, so it becomes colorless. Zn2 plus, no any unpaired electron, this is colorless. We can see 0 unpaired electron is there, so it becomes colorless. But if there are unpaired electrons from 1 to 9, it becomes colored. So we can see 1 unpaired electron is there, it is purple color, then 2 unpaired electrons are there in case of vanadium. So just don't remember this table, because this table is not expected from the student. But why this D block elements are colored, this is expected. So if the unpaired electron is not there, it becomes colorless, and if the unpaired electron is there, it is colored. This concept is required from the student point of view. So the student should not remember this color. One unpaired electron is violet or light pink, and then pale green, and this is green, blue color. Like this, these colors are also not expected, but only the concept is expected. If there is no any unpaired electron, it will be colorless. So the first factor I have completed here. Then the second factor is color explanation on the basis of DD transition. So DD transition is nothing but DD transition means this is a splitting of d orbital. So we can see here this is a 5d orbitals is given. One is a dxy, second one is dyz, third one is xz yz, then dx square minus y square, and this is the dz square. So all these d orbitals are having the same energy level. This is called a degenerate. These are the degenerate d orbitals which is having the same energy level. But what will happen if these d orbitals absorbs the energy from the visible region? When these d transition elements absorbs, transition metal absorbs the energies, means actually this d orbital absorbs the radiations from the visible region. And what will happen due to the absorption, there is a excitation takes place, splitting takes place. So we can see there is splitting is given. So the energy of this dx square y square and dz square, this orbital will be high energy, and this dxy, dxz and dyz, these orbitals having the lower energy. This gap is very small, remember. Though in this diagram, this graph, this gap, we can see the large gap is shown, but actually in practice this gap is very small. And due to this splitting, the color changes, remember. So if the splitting of d orbital takes place, the color will change. So one example I have given here, the titanium. This is a coordination compound. Now we are familiar with this coordination compound. This is inside the square bracket. It is a coordination sphere. Titanium is the central metal atom, and these are the 6 H2O ligands are there, and this is a oxidation state. So it is a cationic ligand, cationic complexes, as there is a 3 plus charge is there. So one coordination compound is there, and titanium, you know, this is a element from the transition element. This titanium H2O6 3 plus, it is purple color. That's why I have shown it is in purple color. So this purple color, how it acquires the purple color, I will explain, and I will stop. Again, the second lecture will be there at 11. What is our timing? 11:10. So again 11:10 we will continue the color part. I will explain this example and I will stop here. So titanium H2O6 3 plus, it is in purple colored. So we have to write first the electronic configuration of this titanium. You know, scandium, it is 21, titanium having the atomic number is 22. The outermost electronic configuration of titanium is 4s2 3d2. 4s2 3d2. But we can see here titanium 3 plus means 3 electrons we have to remove. 2 electrons will be removed from the 4s2 and 1 electron from the 3d. So 1 electron will be remain, 1 unpaired electron will remain in 3d orbital. So titanium 3 plus having the 3d1 configuration. Why this 3d1? Because already 3 electrons are given. 3 electrons are given. So this 1 electron in this dd, so this 1 electron will be here in this orbital, dxy orbital. Then if this 1 electron absorbs the energy, what will happen? This complex ion will absorb the suitable wavelength of white light and promote the electron from lower energy to higher energy level. It will be promoted from lower energy level to the higher energy level. So this promotion is due to the absorption of light from the visible region. So this example is given. This complex, this titanium H2O6, please, this complex absorbs the light around 500 nanometer region. So this is a particular wavelength of the visible region. We can see this is a different regions, visible regions are shown. So this is green and yellow light is there. So this complex absorbs this green and yellow light, and these are the complementary colors. If the yellow light is absorbed, then violet light will be given. If the red light is absorbed, then the green light will be given, or green is absorbed, the red is given, orange is absorbed, the blue is given, or the blue is absorbed, the orange. These are the complementary colors. Already we learned in the school level also what is meant by complementary colors. So in this complex absorbs the mixture of green and yellow color, and it appears as a violet color, purple color. So the color of the complex titanium H2O6 3 plus appears as a purple color. So purple color, it is a color, complementary color actually. The absorbed colors are these colors. Green and yellow colors are absorbed, and it gives the complementary color. Actually, this mixture of red, because green color is also absorbed, so its complementary color is red, and the complementary color of this yellow is violet. So it gives the mixture of red and violet color. So it appears as a violet color, remember. And the solution is purple in color. So this example also, it will be not asked for the examination because it is not given in your textbook. Whatever the examples are given in your textbook, it will be asked, but for your understanding purpose, I have given this example. And then I am coming to this color of the transition metal. 2 minutes are remaining. I will complete this part and I will stop. And in the next lecture, we will continue the next part, that is alloy formation, then interstitial compounds. Interesting part is also remaining. Then we will continue to the lanthanides, actinides, properties of lanthanides and actinides. So one more factor is there. So we discussed this presence of unpaired electrons. Unpaired electrons are there. They shows colors. Also DD transition means there is a splitting of the orbital. Then we will discuss these 2 points: nature of the ligands attached to the metal ion and geometry of the complex. So for these two, I will discuss with one example. When cobalt chloride, when it is dissolved in water, it forms pink solution, remember. This complex is formed. When cobalt chloride is dissolved in water, we get this type of complex. This is a coordination compound, which is having the octahedral geometry. See, if it is dissolved in water, it pink solution and octahedral geometry. The same cobalt chloride, if it is dissolved in concentrated HCl, it forms blue complex. See, blue complex, and the geometry is also changed and the complex is also changed. See, so this cobalt chloride, when dissolved in water, the solution is pink colored, and this is a complex. If the same cobalt chloride is dissolved in concentrated HCl, the solution becomes blue because the complex also changed. This is the complex and geometry also change. So if the ligands are changed, so the ligands are here, your water ligands are there, the color is different. When